We've discussed linear regression and logistic regression and neural networks, and now we're going to learn about an entirely new kind of model, which is called a decision tree. Decision trees can be used for regression or for classification. And so I want to explain what is a decision tree and how do we use them for regression and classification. To put decision trees in context, let's review the setup for just linear regression or for logistic regression. In other words, let's review the setup for training a linear model. We're given a training data set that consists of feature vectors x1 through xn and corresponding target values y1 through yn. Now, if we're doing regression, then these target values y1 through yn would just be scalars. A classic example is we're predicting the selling price of a house. Xi is a feature vector that describes the ith house in our training data set, and yi is the selling price of the ith house in our data set. If we're doing classification, then typically yi is the target values yi are either 0 or 1. And if we're doing, that's for binary classification. If we're doing multi-class classification, then the target value yi would be a vector. If you have k classes, yi would be a one-hot encoded vector that tells you which of those k classes the ith training example belongs to. This is our setup when we're training a linear model. It's the same setup that we often have in machine learning. It's the same setup for when we train a neural network. And when we're doing linear regression, our goal, as we have discussed, is to find coefficients beta 0 through beta d such that yi, the ith target value, is approximately equal to this weighted combination of the numbers xi1 through xid. These numbers xi1 through xid, those are the components of the feature vector xi. Those are the features that describe the ith training example. If we're doing predicting the selling price of a house, then these numbers xi1 through xid, those are the features that describe our house. In linear regression, we want this selling price, yi, to be approximately equal to this weighted combination of our features. And this should be true for all of the training examples in our training data set, hopefully. And in logistic regression, we predict what we predict is a probability. So we take this weighted combination of the features, xi1 through xid, we take this weighted combination and we plug it into the sigmoid function. As we know, this sigmoid function is useful in machine learning because it converts a real number into a probability. And the predicted probability that we get this way, we hope that it agrees with the ground truth probability, which is either 0 or 1. And we hope that's true for all the examples in our training data set. How do we find these coefficients, beta 0 through beta d? How do we find them? Well, we choose these coefficients to minimize this objective function. You can think of each of these coefficients, beta 0 through beta d, that they're like little knobs that we can tune. We can tune these knobs, turn these knobs to improve the accuracy of our model. And specifically, we want to find the coefficients beta 0 through beta d that minimize this cost function. And what's happening here is that yi is the target value for the ith training example. F sub beta of xi is our predicted value. We hope that our predicted value agrees with the target value. This function L, this is our loss function, it measures how well our predicted value agrees with the target value. And if we're doing regression, then we use this quadratic loss function. And if we're doing binary classification, then we use this cross entropy loss function. In machine learning, how do we compare two probabilities? We use the cross entropy loss function. And so that's the setup for linear, when we're training a linear model. It could be for regression, it could be for classification. This is what we do when we train a linear model. This is the pattern. And when we motivated neural networks, we said, can't we choose this function f sub beta more creatively? Does it have to be just an affine function? And here in this linear model, f sub beta is a linear function or an affine function. That's about as simple as f sub beta can get without being totally trivial. Can't we get more creative? What if f sub beta is a nonlinear function? And then that was the question that we used to motivate the introduction of neural networks. We said, what if f sub beta, instead of this simple affine function, what if it's a neural network? And then that led to neural networks, and we learned all about neural networks. Now, here's a completely different choice of of f sub beta. F sub beta could be a decision tree. So instead of a linear model, instead of a neural network, f sub beta could be a decision tree. That's a completely different type of nonlinear function. And so this is by thinking about this question, how do we get more creative with our choice of this function f sub beta? That question could lead to neural networks, or now it's leading to decision trees, which is our new topic. So let me explain what a decision tree is. So here's an example of a decision tree. Let me just give you an example. This decision tree, this diagram, describes a function. And this function takes a feature vector as input, and it returns a number as output. And in this example, we're predicting the selling price of a house. Each of these little red figures here, they look kind of like a house. Each of these little red figures is supposed to represent one house in our training data set. So in this example, our training data set consists of 7 houses. And let me show you how this decision tree works. This decision tree describes a function. This function takes as input a feature vector that has 2 components, x1 and x2. 2 components only. This is a simple example. So our feature vector has only 2 components. And what the function does is first it looks at the value of x2, which is the second component of our feature vector. If x sub 2 is less than 3, then we move here. And if x sub 2 is greater than 3, we move here. And now if we end up in this bin, if we end up here at this node of our tree, this is called a terminal node, then we're done. We stop there. On the other hand, if we end up here at this node, what we do next is we look at the first component of our feature vector x. If that first component is less than 5, then we move to this node. And if that, on the other hand, if x1 is greater than or equal to 5, we move to this node. And so, okay, so that's how our decision tree works. And if you take all the examples in our training data set, and you run each example through the decision tree, then in this example, we end up with two training examples end up here at this terminal node. 3 training examples end up here at this terminal node. And then 2 training examples end up here at this terminal node. This decision tree that we have a diagram of here, this decision tree has 3 terminal nodes, here, here, and here. If you take each of the training examples and run them through the tree, 2 of the examples end up here, 3 of the examples end up here, 2 of the examples end up here. We have 7 examples in all. Okay, now, I haven't fully described how this function works. If I take a feature vector, x1, x2, the components of my feature vector x are x1 and x2, and I plug that feature vector into this function, into this decision tree function, what's the output? Well, that depends. Here's what we do. We take our feature vector x, we run it through the decision tree. If we end up here, then what's the output? If we end up here, then the output is the average selling price of the 3 houses from our training data set that end up in this node. So the output of our function, if x ends up here in this node, then the output is the average selling price of these 3 houses. In this example, that average selling price is $332,000. And on the other hand, if we take our feature vector x and run it through this decision tree, and if we end up here, then the output of our function is the average selling price of the houses in our training data set that ended up at this node. In this example, the average selling price of the houses that ended up in this node is $374,000. And finally, if we run our feature vector x through the decision tree, and if we end up here, then again, as before, the output of our function in this case is the average selling price for these two houses. These are the two houses in our training data set that ended up at this node. In this example, the average selling price of these two houses is $213,000. So that's how this function works. A decision tree is just a function. You give it a vector x, you give it a feature vector x as input, and it gives you a number as output. To make this more concrete, let's figure out what would be the output of this decision tree function t. We're calling this function capital T. What would be the output if the input is this feature vector 2, 6? To figure that out, let's take this feature vector 2, 6 and run it through the decision tree. So here at the first step, we have to look at the second component of our feature vector. We have to look at x2, the second component. And the second component of this feature vector is 6. Since 6 is greater than or equal to 3, 6 is greater than or equal to this threshold value 3, that means we move here. We move to this node. Okay, good. That was the first step. Now, the next step is to look at x1, the first component of our feature vector. The first component of this feature vector is 2. And since 2 is less than 5, 2 is less than this threshold value 5, that means we move here to this node. And this node is a terminal node, so we stop here. And so the output of our function is 332,819. That's the output of this function when the input is this vector 2, 6. Okay, now let's figure out what's the output of this decision tree function t if the input vector is this feature vector 4, 2. So first we look at x2, we look at the second component of this vector. That second component is 2. Since 2 is less than 3, we move to this node here. This is a terminal node, so we stop. And the output of our function is 213,712. So that's how a decision tree function works. You can also use decision trees for classification. And let me show you how it would work in a classification problem. Here we have a diagram that represents a decision tree function. And now in this example, our training examples come in, they each belong to one of two classes. There's a star class, which we see some of our training examples are red stars, and there's a circle class. Some of our training examples are green circles. And the output of this decision tree function is going to be a probability. It's going to be the probability that the input vector belongs to the star class. So the output of this decision tree is going to be a probability, and we're going to see how that happens right now. So let's figure out what is t of 3, 2. If the input is this feature vector 3, 2, what is the output of this decision tree function? Well, the way this decision tree works is first we look at x1, which is the first component of our feature vector. In this case, x1 is equal to 3. Since 3 is greater than 2, that means we move to this node here. Okay, next we need to look at x2, the second component of our feature vector, and x2 is equal to 2. Since 2 is less than 4, 2 is less than this threshold value 4, that means we move to this node. And this is a terminal node, so we stop here. Now, if we look at the training examples, which ended up in this terminal node, then 3 of them are stars, 1 of them is a circle. So our predicted probability that the feature vector we're looking at belongs to the star class, our predicted probability is going to be 3/4. So that means that in this example, when the input is this vector 3, 2, the output is 3/4. That's a probability. That's our predicted probability that the feature vector we're looking at belongs to the star class. Okay, what if the input vector is this feature vector, 4, 7? Then what is the output of our decision tree function in this example? Let's take this vector 4, 7 and run it through the decision tree. First, we have to look at x1, the first component of our feature vector. x1 is equal to 4. 4 is greater than 2, so that means we move to this node. Next, we look at x2, and x2 in this example is 7. And 7 is greater than 4, so that means we move to this node. And here in this node, if we look at the training examples that ended up in this node, 2 of those training examples belong to the star class, 1 of them belong to the circle class. And so that means our predicted probability that the feature vector we're looking at belongs to the star class, our predicted probability is 2/3. So the output is, in this example, is 2/3. Okay, finally, what if the input feature vector is 1, 6? Then what's the output? Well, again, we start by looking at x1, the first component of the input. Since x1 is 1 and 1 is less than 2, that means we're going to move to this node here. And this is a terminal node, so we stop. In this terminal node, if we look at all the training examples that ended up in this terminal node, 1 of them is a star and 4 of them are circles. So that means our predicted probability that the feature vector we're looking at, it belongs to the star class, our predicted probability is 1/5. So that's how a decision tree works for binary classification. It gives you a probability. So decision trees can be used for regression or for classification. And by the way, even though in this example, at the first decision, we're looking at x1, which is the first component of x, it doesn't have to be that way. We don't have to start by looking at the first component of x. In fact, on the previous example, we started by looking at the second component of x. So you don't have to look at the components of x in order. That's not how decision trees work. Okay. Here's another example of a decision tree. In this case, we're trying to predict the salary of a baseball player. Actually, we're trying to predict the log of their salary. And the way that this decision tree works is first you look at how many years the player has been playing. If it's less than 4.5, then your prediction is 5.11. If the player has been playing for greater than 4.5 years, then you move here. And then you look at how many hits the player got in their previous year. If they got less than 117.5 hits, then this is your prediction. You predict that the log of their salary is 6. If this player got more than 117.5 hits the previous year, then this is your prediction. You predict that the log of their salary is 6.74. And here's a more complicated example of a decision tree. You can see decision trees can get pretty complicated. They can have many stages. They can be deep. And so let's look at how this decision tree works. So we start off again by looking at the number of years the player has been playing. But then here we're looking at this RBI statistic. This is just one of the statistics you can compute to measure the performance of a baseball player. And then let's say that their RBI statistic is greater than 60.5, then we move here. And now here we're looking again at years. So just because we looked at years already when we started out, doesn't mean that we're forbidden from looking at years, the number of years playing again. We can look at it again. So here we check if this player has been playing less than 3.5 years, then you make this prediction. If this player has been playing greater than 3.5 years, you make this prediction. So there's no rule that just because you looked at years already to start with, that doesn't mean you can never look at years again. You can. So this is just a more complicated example of a decision tree. Okay, So now let's talk about how do you train a decision tree? If we're given a training data set, then how do we train our decision tree? We're given a list of feature vectors and a list of corresponding target values. What do? Well, just like before, we want to minimize this cost function value. We just use the same strategy. We want to find a decision tree that makes this cost function as small as possible. Here, yi is the ith target value in our training data set, as we discussed. T of xi is our predicted value. This loss function L measures the agreement between the ground truth value yi and our predicted value T of xi. We want this, if this loss function value is small, that means our prediction agrees closely with the ground truth value. So we hope this whole sum is small. That means all of our predictions agree closely with the ground truth values. This is just our standard setup for training a machine learning model. And as we mentioned before, if we're doing regression, then our loss function is going to be this quadratic loss function. If we're doing binary classification, as we mentioned, then our loss function will be this binary cross-entropy loss function. That's what we use when we do binary classification. This is just the same recipe that we always follow in machine learning. There's actually one problem with minimizing this objective function, which is that the decision tree we get, if we try to minimize this objective function, might overfit the training data. We encountered overfitting constantly when we were training neural networks, and we have the same problem here when we're training a decision tree. We have to guard against overfitting. And we can guard against overfitting by introducing this regularization term into our cost function. This regularization term is proportional to the number of terminal nodes in our decision tree. So what this regularization term is doing is it's discouraging us from finding a decision tree that has too many terminal nodes. If our decision tree has too many terminal nodes, then this regularization function is going to punish us for that. This regularization function wants a nice simple tree that doesn't have too many terminal nodes. So this regularization term helps to control the complexity of the decision tree that we find. And if we use a less complex decision tree, then we are less likely to overfit the training data. So how do we go about finding a decision tree that minimizes this cost function? We can't use gradient descent. Even if we did write out a parameter vector beta that specified our decision tree, it would be unclear exactly how to write like a formula for the output of our decision tree in terms of that parameter vector. It would be even less clear how to take the derivative of that function. And so how do we take the derivative of a decision tree function? That is something that we can't do. So that means we can't use gradient descent. So instead, we use a different optimization algorithm. And what we do is we take a greedy approach. And here's how that works. Initially, our decision tree contains only a single node, and this single node contains all the training examples. In this example, we have 7 training examples. Each training example looks like a little tiny house here. We have to decide, first of all, how do we split this node? And how do we make that decision? Well, what we do, we have to figure out 2 things. First of all, which feature should we look at when we're splitting this node? Which feature should we look at? Should we look at X1? Should we look at X2? Should we look at X3? Which feature do we look at? We also have to decide what threshold should we use when we're making this split. So how do we make these decisions? We make them in a brute force manner. We look at all the features, and for each feature, we consider all the possible threshold values S. And we see for all of these possibilities, which possibility gives the greatest reduction in the value of this sum here. This sum does not include the regularization term. At this stage of training, at this stage of growing our decision tree, we're ignoring the regularization term, and we're only trying to find the split that minimizes this sum as much as possible, that reduces this sum as much as possible. So we choose the feature and the corresponding threshold value for that feature. that reduces this sum as much as possible. We make those decisions in a brute force manner. We just use exhaustive search. We try all the features. For each feature, we try all the threshold values S, and we see which of those options gives us the greatest reduction in the sum here. Now you might ask, for a given feature, how do we try all possible values of this threshold S? Aren't there infinitely many possible values, and how could we try infinitely many different values for S? But the answer is that our training data set is finite, so actually we only need to try a finite number of different values for S in order to see which one, in order to get the best threshold value for that particular feature. So that's how we decide how to split the first node in our decision tree. And what do we do next? Well, then we look at this node here and we figure out how to split this one using the same procedure. And we figure out how to split this node using the same procedure. And so it's just a recursive process. Each time we split a node, we split it in whatever way reduces the value of this sum as much as possible. So growing a decision tree can be done recursively. If we were writing a computer program to grow a decision tree, we could start by splitting this initial node, and then we could call our tree growing function on each of the two child nodes. And how do we know when to stop? Typically, we use a stopping criterion such as this one. If we reach a node that has fewer than 5 training examples that belong to that node, then we stop and we declare that node to be a terminal node. And notice that during this stage of training, during this stage of growing our decision tree, we have been ignoring the regularization term. The decision tree that we get as a result of this growth process so far might be overly complex. So next we need to prune our decision tree in order to reduce its complexity. In the pruning stage, we no longer omit the regularization term. Now the regularization term is included. Now we're paying attention to the regularization term. And what we do in the pruning stage is we start with our decision tree, which is overly complicated, and then we look at all possible subtrees, and we choose the subtree for which this cost function is as small as possible. And that's our pruned decision tree. And that's the final result of our training process. This parameter lambda controls the complexity of our final decision tree model. If lambda is large, then we are punished severely for having a decision tree with many terminal nodes. So we'll end up with a very simple model that doesn't have many terminal nodes. On the other hand, if lambda is small, then we're free to use a more complex decision tree with more terminal nodes, and we won't be punished too severely for that. Now let's talk about the pros and cons of decision trees. One point in favor of decision trees is that they are easy to explain to people. They're easy to interpret. You can explain them to your manager. You can explain them to the CEO of your company. Even if they don't know anything about math or machine learning, they'll still be able to understand the decision tree process. A lot of times in medicine, doctors might not want a patient to be diagnosed using some opaque machine learning procedure like a neural network because you can't understand why it made its decision. Whereas with a decision tree, you can understand the thought process. You can understand the sequence of steps that the algorithm went through to arrive at its decision. Another advantage of decision trees is that they're able to handle categorical variables directly without using one-hot encoding. When you're growing your decision tree and you're trying to decide how to split a particular node, you look at all the features, and some of those features might be categorical. So let's say that we're looking at a categorical feature. How do we split based on a categorical feature? It doesn't make sense to choose a threshold S in this case, but here's what you can do. Let's say that your categorical feature has 4 possible values, for example. You can just consider all possible ways to take those 4 values and split them into 2 distinct groups and see which of those ways gives you the best split. The major downside of decision trees is that often the prediction accuracy is not high enough. But often the prediction accuracy can be improved greatly by combining many decision trees into one single model. And that leads to 2 different strategies that are very important. One is called random forest. The other is called gradient boosting machines. These are ways to combine many decision trees into one single model. Back around 2012, before deep learning became so successful, These two methods, random forests and gradient boosting machines, were very dominant in Kaggle competitions. They were winning many Kaggle competitions. And these two methods remain two of the most important and most effective machine learning algorithms.